Dr. Umans was talking about uniquely solvable puzzles, and he stated that this is a nomenclature that's used only at the Caltech campus. But then I went ahead and I dropped this into Google, and there was a bunch of research papers that came up, a lot of them referencing work from Dr. Umans, and they were using the same title, right? So you can go ahead and dig into that if you'd like to see if you can get some more information. And so what I want to say is that, as he was describing the puzzle and describing the situation, I myself, I didn't really understand exactly what he was talking about. I wanted to ask questions, but I didn't want to interrupt him. And I feel that many of you also felt the same way. And so I went ahead and thought about it a little bit, and I think I got a pretty firm grip on what the problem is. And so I want to just communicate that to you and see if that's something that we could think about before we meet with him 2 weeks down. And so what we have here is a grid, right? So basically a 2D array. And the grid, let's say, has a set number of columns that we can call W. Let's say W is 4. And then a set number of rows, which we can call N. That we can call N. And let's say the bottom row here is N. And then the one right there is N minus 1. And we dot, dot, dot up to the top. And of course this is 0 and 1. And then we're going to split this guy into 4 columns, and the elements in the 2D array can be 1, 2, or 3. And so let's go ahead and just fill this up with some values, and let's take a look at what the problem is exactly. And I wanted to say that even if my understanding is incorrect, it would be nice for us to understand what I'm saying, and then kick that around. And then, even though it's a misunderstanding, then Dr. Umans can clear that up when we meet with them again, and we will have thought about it, and we'll have a better, ability to manipulate these kinds of ideas, right? So even if my understanding is incorrect, it's a helpful exercise for us, right? So let's go ahead and fill this up. We got 3, 1, 2. We got 1, 3, 2, 1, and the rules of the game here are that you can swap out numbers from one row to another row, but only if they are in the same column. So for instance, we could swap out this one and this one here with another column that has only a 1 in the 0 column and a 1 in the 3 column. So if we compare row 1 and row 2, these cannot be swapped out because there is no 1 in the 0 column, there is no 1 in the 3 column, and there is a 1 in the 1 and 2 column, which is not the case in row 1. So these cannot be swapped out. Let's look at n minus 1, cannot be swapped out for the same reason. Let's look at the row n, it can be swapped out because the 1s are able to switch, right? The 3s are not able to switch, or the 2, but the 1s can switch. And because the 1s can switch, this puzzle is not uniquely solvable. Okay? So what is a uniquely solvable puzzle? It's one where you cannot switch any numbers of any rows with any other rows following those rules. And so when you look at that problem, you might think to yourself, well, first of all, you might think to yourself, like, who cares about this problem? And so what we need to do is take faith in what Dr. Umans was saying, is that solving this problem will lead to a faster method of matrix multiplication, which has immense ramifications for the real world, right? And he illustrated one of them during class. And so we want to go ahead. The next thing that you want to think about is, okay, well, here's the problem, but how can I begin to solve this, right? How can I even begin to think about this? And what was the problem? The problem is given a number W and a number W and a set number of values that can be placed inside the 2D array, what's the maximum number of rows that this 2D array can contain where the puzzle can remain uniquely solvable, where you cannot switch any numbers from any rows with any numbers from any other rows. And so when you think about these kinds of problems, some of us are just kind of maybe have a higher aptitude for abstract thinking, right? And so some people can look at this problem and just start writing equations down, describing the problem, and manipulating those equations in order to come to a solution. And I'm not one of those people, right? And so you folks might be, but most likely you're not. And so what you want to do here is look at a very simple case, the simplest case, and then describe it mathematically, right, using these variables like n and w, and then increase the complexity and describe it, increase the complexity and describe it, increase the complexity, describe it, and then try to find a pattern so that you can extrapolate like a mathematical equation for n in which the puzzle will remain uniquely solvable. All right. And so like one example that I kind of want to put forth is the worm. I'm not sure if you took the Intro to Computer Science class, but it's the JavaScript class here at the school, and one of the problems is the worm problem, right? And so what's the worm problem is that we have circles that were one side of the circles touch the right side of the screen, and then the last circle's right side touches the right side of the screen. The width is w, and the number of circles is 15. Right. So what the problem is how do we figure out what the radius of these circles are, right? And so if you think you have like a high aptitude for thinking abstractly, or maybe you've seen this kind of a problem before, and you have some experience with it, you're able to just solve it. But for the most of us, we would need to kind of look at simpler situations, and then try to find a pattern, right? So let's say the simplest solution is one where n is equal to 1. Right? And if that's the case, then the left side touches the right side of the screen, the right side touches the right side of the screen, and what is the radius of the circle? Well, then radius is equal to w divided by 2, right? So if width is 100, then that means the radius of this circle is 50. And then if we go ahead and take a situation where n is equal to 2, the next most complicated situation, and we have something that looks like this. I'm drawing this incorrectly, but let's assume that they're touching each other. Well, then what's radius? Well, radius is right here, and here's w, right? And we basically need to count the radiuses as we go across. So there's 1 radius, 2 radius, 3 radius, 4 radius. So w is equal to radius is equal to w divided by 4, right? And then we go ahead and draw another case where we have 4 circles across the screen, and n here is equal to 4. We got w up at the top, and then what's radius going to be in this situation? Well, it becomes pretty obvious that w is going to be equal to radius is going to be equal to w divided by 8. And so as we look at the situation, well, can we come up with a expression for r involving n, because n is the dependent variable here, right? The number of circles that are on the screen is what's going to determine the radius of the circles, right, according to the rules of this situation. And so if you look at it, well, it should become clear after looking at it for a bit that it's w over 2 times n, right? And so we go ahead and guess this expression. And then we go ahead and test it out, right? Over here, it's w divided by 2 times 1, w divided by 2. That works, great. We come down here, it's w over 2 times 2, n, that's 4, it works here. And then over here, we got w divided by 2 times 4, which is 8, so it works, right? And then we go ahead and code it, and we find that it actually does work, and we're happy, right? So this is kind of an approach that you might want to take as you look at and think about this problem over here, right? And so what's a pretty simple example of this problem? Well, it's one where w is equal to 1. Right, and then the problem is how many possible n's can there be where we could still be uniquely solvable? And so if there's n is equal to 1, well, then it's definitely uniquely solvable, because if there's only one element, you can't switch it with anything else. And so if there's 2, then it's uniquely solvable as well, because we could have 1 and 2 there, right? So that's a uniquely solvable puzzle. If there's 3, we can go uniquely solvable, right? But we can't put another one, because another one would require that we put 1 or 2 or 3 here, right? And so if that's the case, then we could swap those 2 out, and it would not be uniquely solvable. So in this case, the max is equal to 3, right? The max n. And so the next most simplest situation here would be where W is equal to 2. And so we'll take a look at this, right? And so now you'll notice that when W increases, the maximum number of rows of n also will increase, right? And kind of like an exponential type of curve. And so what you kind of want to think is, how many n's can there possibly be where adding another n will make it impossible to contain a uniquely solvable puzzle in this situation, right? And so you figure that out. Okay, great. And then let's try it. W equals 3, W equals 4, W equals 5, W equals 6, right? And then take a step back and take a look at it. See if there's any patterns. See if you can figure out what is the equation involving W, right? And possibly the number of characters that you can use to describe the max number of rows that you can contain while still maintaining the property of containing a uniquely solvable puzzle. And so I guess that's all I need to say about that. And good luck with thinking about that problem.